Be kicking things off here. It's a great pleasure to join you all. Thank you for joining from your various time zones. I want to begin by thanking all of my collaborators who've made this such an exciting venture. So former students, some of them now, of course, faculty and collaborators, including Anand. All of the people highlighted in yellow here will be speaking later. It's been a great pleasure and honor to work with all of you. I also want to thank my funding sources, NSF, LSI, Marie Curie Foundation, and the Marc Fleury Foundation. So I just want to do a brief history. So of course, Yves and Emmanuel discovered the bouncing drops around 2005, and we were a little slow to the party at MIT. So 5 years later, we started meeting, and the first HQA meetings were in Paris. So it was just our group and Yves' group with Emmanuel there. And so that was the first two. Then we went to Boston, went to Rio. We had some really fun meetings, Calabria being my favorite. And they've so that's now been going for 10 years. And as I said, this was, HQA 9 was to be in Lisbon. Now we're in Zoomlandia. And I just wanted to note that 2024 is coming up. So that's the centenary of Debray's thesis. So that would surely hearken a return back to Paris. If not, I'll be happy to do it in Boston. But so 10 years ago, so when at our time of our first meeting, there were 3 groups working on HQA. There was, of course, the founding fathers in Paris, and then the group at MIT, and also a group in Liège had been working on it for some time. And now by looking at the author list of the latest review, oops, what's happened? Yes, I was able to track the how the research activities in HQA have evolved in the last 10 years, and now we see stars all over the place, and long may that continue. And by the way, if any of you know of stars that I've missed, or that my star is misplaced owing to errant geography, please let me know in the chat. Okay, I'm having trouble advancing here. Okay, so right, so what is so quantum mechanics? We think in terms of a theory that describes statistics of microscopic particles, but it fails to describe their trajectories. So the description of the free particle is simply an association of a particle with a wave. So of course, when you're an undergraduate, you ask, but where is the particle and why does it move? So now the insistence on the completeness of trajectory-free quantum mechanics has led to long-standing difficulties, in particular the proliferation of quantum interpretations, and our philosophers, friends in the audience are better qualified to talk about that, and also an abundance of paradoxes and troubling language. Now, the history of science has shown us that paradoxes in science indicate that the workers in the field are viewing the problem from a wrong or unhelpful perspective, that their premises are unacceptable. So for example, in fluid dynamics, there was a long-standing paradox called D'Alembert's paradox, which lasted actually for 150 years, which resulted from an inability to resolve the viscous boundary layer. So there's basically a dynamics on a scale which had not yet been resolved. And once it was, then all of the paradoxes disappeared and modern fluid dynamics was born. And what the wonderful thing about the walking droplet problem is it really brings a fresh perspective to the quantum paradoxes, and suggests, as we'll see, that the quantum paradoxes may ultimately be resolved through the elucidation of a pilot wave dynamics on the quantum scale. Okay, so what are hidden variable theories? So these are theories that try to account for particle trajectories. So you basically have a dynamics underlying the quantum statistics, which is of course well described by quantum mechanics. And it turns out that as far as I know, these hidden variables all involve a particle interacting with a wave. So we have de Broglie's pilot wave theory, which involves the particle generating a wave and moving in response to it in such a way as to give rise to a statistical behavior consistent with that of standard quantum predictions. And then Bohm presented a single wave pilot wave theory where basically the wave function is guiding the particle. And then Nelson proposed the stochastic dynamics, which suggested that quantum mechanics can be understood in terms of a diffusive process with a diffusivity given by h bar over m, which is basically the particle speed times the de Broglie wavelength. And we'll see, and then finally, we'll hear from Anna Maria later, but De La Peña and Cheto have developed a stochastic electrodynamics in which a pilot wave is sought in the electromagnetic quantum vacuum. And we'll see that this sort of, these physical pictures, which they invoke, all have the bouncing drop problem touches on all of them. Okay, and so this began in 2005. So Yves Coudert and Emmanuel Faure discovered this hydrodynamic pilot wave system in which a particle moves in resonance with the guiding wave. And this resonance condition, as we'll see, is very important. And this is really the first macroscopic realization of the double solution pilot wave theory proposed by de Broglie, and it exhibits several features of quantum systems thought to be exclusive to the microscopic realm. So the questions raised: what are the key dynamical features responsible for the quantum-like behavior? And we understand that now. And what are the potential and limitations of this hydrodynamic system as a quantum analog? And that we're exploring currently. That is, when I say we, I mean the entire community of HQA. And can it guide us towards a rational theory for quantum dynamics? Okay, so the physical system of interest is this is a vibrating bath. So we vibrate this bath, and there's a vibrational acceleration above which, when this exceeds a critical value, which is about 4.5 times gravity, you excite Faraday waves on the free surface. So the experiments are actually done always. Is this, by the way, is this little tag here, this green tag is annoying me. Can you see it, or is it just me? For that matter, is anybody home?
No, we can see it.
Yeah. Don't worry.
Let me just. Why is this?
I think you can drag the whole bar away.
Yeah, you can.
Just drag it with the mouse.
Take care of it. Okay.
No,
Oh, it didn't work.
okay. It's good.
Right, and so the Coudert Walker, this involves putting a millimetric drop on the surface of this vibrating bath, but below the Faraday threshold. So in the absence of the drop, there would be no waves. Now, a key feature of this is the particle is actually resonant with the wave that it excites. So it's bouncing. The waves are subharmonic, so it's bouncing subharmonically relative to the driving. But because you have this resonance, the waves are particularly long-lived. So it's like you're forcing the system at resonance. So the waves are very long-lived, and it's the waves that give rise to this so-called memory effect. So in order to calculate the instantaneous force on the drop, you have to evaluate the local slope of the wave field, and that involves integrating backwards in time to get the contributions from all of the impacts, okay? And the closer you are to the Faraday threshold, then the more persistent the waves are on the surface and the longer the system memory. And it's this notion of path memory, which is really critical in giving rise to effects that appear to be, that one can misconstrue as being non-local, okay? Okay, and so in fact, this class of dynamical systems with memory, this is called hereditary mechanics. It was first looked at by Volterra and Brillouin. These are not terribly well mined in even in classical mechanics. And we'll see again how local hereditary mechanics can give rise to behavior that appears to be spatially non-local. In particular, we'll see that there's something analogous, roughly analogous to the quantum potential arising through the system memory. Okay, so this arises the memory in the trajectory. So if you look at the trajectory equation, sorry, of the bouncing drops, you have the inertial term, you have a drag term, and the interesting term is this wave force. So, and it's here that the memory appears. So this memory, this is the timescale viscous damping of the waves, and this is the Faraday period, and this is the vibrational acceleration. So as this approaches the Faraday threshold, the memory becomes very long, and the waves are very persistent because it's this memory term which appears in the damping term of the wave. So basically each impact, it generates a Bessel function with some spatiotemporal damping. And the closer you are to threshold, the more long-lived the waves are. And all of the hydrodynamic quantum analogs involve operating at high memory, where the waves are most persistent. Okay. And so this also gives us, there's a nice little feature which also harkens back to de Broglie's mechanics, which is that because we have resonance between the particle and the wave, you basically wind up with a particle which is dressed with a quasi-monochromatic wave, right? So here we grab an image per bounce. So you just see the thing gliding along, and we can describe, and so basically strobing in this system at the bouncing frequency is roughly analogous to strobing in de Broglie's mechanics at the Compton frequency, okay? And so again, you have this particle dressed in a monochromatic wave field. Okay, so we can actually describe the dynamics in this strobe. We can so throw out the vertical bouncing and now just describe the horizontal dynamics, and this then reduces to an integral differential equation. So you imagine the particle is a continuous source of waves, and this integral differential equation is nice in that it's amenable to analysis, so you can assess the stability of various dynamical states, in particular the transition from bouncing to walking, and so forth. And so we've used this for looking at the stability of various bouncing droplet systems here, including orbiting pairs and these promenading pairs, and more recently some exotica. So if you start with a ring of drops and you increase the vibrational acceleration, that's always the sort of control parameter, then it goes unstable to these various modes of motion. And we can actually predict this theoretically using the strobe model. We have to modify it to take into account the variations in impact phase for some of these systems. Okay, so let's get on to HQAs, which is the subject of particular interest. So this is again all started by Yves Couder and Emmanuel Faure. I think this is a seminal and really important experiment looking at Walker diffraction. So as a Walker approaches a slit, it is deflected in some fashion. It may be unpredictable. It may not be, depending on what the memory is, but you basically get this this wave-like statistical behavior. So you can associate this, you can describe the statistics in terms of a wave. So this is the deflection angle. This is the incidence of that deflection angle. And so you see this three-peak structure. And so we went back and Giuseppe did a very painstaking series of experiments, and he basically recovered this three-peak structure. And in fact, people have gone back, the most refined experiments were recently done by Ellegard and Levinson. They actually had a thermal control on their baths, so the most precise results yet. And they basically got the same thing. You get this three-peak structure. And perhaps most importantly, in the case of the double slit, you see that the particle feels the presence of the second slit, as you can see here. So here we have a single slit, here we have a double slit, and you see that the particle behaves differently as a result of the second slit. That's simply because the particle is dressed in a wave field, and the wave field interacts with both slits, okay? And so there's been a lot of hoopla as to the diffraction pattern being different from that in quantum mechanics, but that fails to disquiet me. In fact, there's little reason to expect them to be similar. In the quantum experiments, the slit is around, certainly for electron diffraction, is about 1,000 times the de Broglie wavelength. Here we have the guiding wavelength is comparable to the slit width. And also, of course, Lord knows what the boundary conditions might be in quantum mechanics. And we know that we expect that to be important in that system, just as it is in ours. But nevertheless, you get this robust wave-like statistics emerging from chaotic pilot wave dynamics. And even in the case where it's not chaotic, you get it. Okay, so another case where sort of non-locality, so you can say that the second slit has a non-local effect on the dynamics. Another case where this is true is if we look at Walker scattering from a submerged pillar. So here we see a Walker approaching from right to left, and there's a submerged pillar there. And we're just thinking, oh, I wonder how it will be influenced by this pillar. And you get a rather remarkable result in that owing to the distortion of its pilot wave field, it actually locks into a logarithmic spiral. And so if you, from the form of the spiral, you can infer what the effective force is. So again, part of the game here is saying, okay, well, let's imagine we don't think it's a pilot wave system. What force would give rise to that trajectory? And here it takes a very nice form. And again, it can be inferred directly from the trajectory itself. And it's a lift force, which is proportional to the velocity of the Walker crossed with the instantaneous angular velocity of the Walker around the center of the post. Okay, so owing to the analogous form of the Coriolis force acting on a mass in a rotating frame and the Lorentz force acting on a charge in a uniform magnetic field, you can see that this behaves like a charge moving in response to its own magnetic field. Okay, so be that as it may, what you do see is, again, if you deny it's a pilot wave system, you would infer that there's a non-local force, right? But in reality, we know that this net force, which takes this particularly clean form in this particular case, is a result of the alteration of the pilot wave by the presence of the pillar. Again, if you deny the fact that the wave is there, you infer non-locality. Okay, and so another scattering problem in Walker's we looked at was an analog of Friedel oscillation. So here we basically, this is in the quantum realm here. So you have a sea of electrons on the left and you have various impurities on the surface. And you see these rings around the impurities. And that's from the electrons in this electron sea scattering off impurities. And they don't have a physical picture for it, but you can solve it using Schrodinger's equation and the appropriate scattering potential. And so here we see, our analog is a Walker approaching a submerged well. These are experiments done by Pedro Sainz. And you can see as a Walker, it's basically drawn inwards to the submerged well along an Archimedean spiral. And as it interacts with the well, its inline oscillations are excited. And so you'll see ultimately the emergence of a coherent statistical pattern owing to the speed variation. So we color code the trajectories according to speed. Red means they're moving fast, blue relatively slow. And because you have these, you can see the concentric rings of velocity. So because velocity is a function of position, you get this emergent statistical form, which looks very much like Friedel oscillations. Okay, so from that one can make the very conservative conclusion that Friedel-like oscillations are not inconsistent with the notion of particle trajectories. Okay, and so the second sort of class of HQAs was again started in Paris by Emmanuel and Yves. This is what Walker's moving in a rotating frame. So if you have something moving at uniform speed in a rotating frame, you expect it to follow an inertial orbit where there's a balance between inertia and Coriolis force. So you expect the radius to decrease with rotation rate, again, assuming the velocity is constant, which is effectively the case for Walker's. And so that's what they find at low memory, but at high memory, you see the emergence of this orbital quantization. And this is in response to the particle moving. So it's basically interacting with its own wake. So it's moving on a corrugated free surface, right? So it's only stable at certain radii. And they drew this wonderful analogy between these quantized inertial orbits and Larmor levels, again, using the fact that the Coriolis force has an analogous form to the Lorentz force. Okay, so here we see very clearly that the Faraday wavelength is playing the role of the de Broglie wavelength. Okay, so we revisited this problem both experimentally and theoretically. And so if we throw in a Coriolis force on our stroboscopic model, then you can basically find the orbits and assess their stability. And so here are theory versus experiments, and you see that these regions where you don't have orbits correspond to regions in which the circular, so radii at which the circular orbits are unstable. So this is the radius of the orbit, this is the rotation rate. So again, this is classical, it looks like a hyperbola. And the quantization is imposed by the wave field. And so we were basically able to rationalize the observed stability of these things. And I think most interesting is what happens when they do become unstable. So when the system becomes chaotic, then instead of having a stable circular orbit, it destabilizes into a series. It basically jumps between unstable circular orbits. And so if you plot the radius of curvature as a function of time, you see that there are preferred orbits. And you see this sort of wave-like statistical form, and the detailed form of the emergent PDF depends on the relative instability of these unstable orbits. Okay, and so, but again, you see sort of wave-like statistics with the de Broglie, with the Faraday wavelength, a signature of the Faraday wavelength on them emerging from chaotic pilot wave dynamics. Okay, and the other thing we noted in this in that paper with Anand was that the one has the possibility, at least, of spin states in which a particle zips around in its own wave field, even in the absence of rotation. So without the confining Coriolis force, there is still the possibility of the inertia of the particle being balanced by its own wave field. So it turns out these were unstable in the parameter regime we were looking in. I think there has been some whisperings of these having been found. I think Marc Fleury with Emmanuel and perhaps others have maybe found these spin states, which would be wonderful for HQA in some other regime. And of course, the possibility exists if you explore, as we learned from the group in Australia, if you look in a different parameter space, you're going to find interesting and marvelous things. So, okay, so that was the first examination of orbital dynamics in this pilot wave system. The other was done in Couder's group also. So Stefan Perard did these experiments for his thesis, and they looked at the particle Walker motion in a central force. And so they found the following periodic orbits. So there's basically a double quantization imposed on the orbits, on the periodic orbits that they found. So they're quantized both in mean radius, which is effectively the energy, and then the mean angular momentum. So mean angular momentum, when that's 0, you have the lemniscates. As you move along these axes here, you see circular orbits, and then at higher, when the spring force is decreased, you get larger, more complex orbits. And once again, so from this sort of basis of periodic orbits, when the system goes chaotic, it switches between them. So again, you see chaotic trajectories with multimodal statistics. Okay, and so the very first HQA we looked at in our lab was this was the quantum corral. So here is similar to Friedel. You have the Friedel system. You have electrons zipping along the surface of a metal, corralled in by these positive ions, which tend to limit the electrons. And so what you see is this sort of the modes of the cavity is the PDF of the cavity is basically, you see the signature of the de Broglie wavelength. Okay, and so with the walkers, we let the thing run, and we again color code the trajectory according to speed, and so you get something very complicated. You think, oh boy, we're not going to get anything coherent emerging out of this. But sure enough, and again, one of the great joys of the system is after about half an hour, or so the time scale of statistical convergence is about an hour. I mean, it could have been a week, could have been a month, but after half an hour, you get a PDF which looks basically like this. So you see, again, the Faraday wavelength playing the role of the de Broglie wavelength, and these coherent wave-like statistics emerging from chaotic pilot wave dynamics. And I just think it's important to emphasize the scale. So the scale of the quantum corral is 75 angstroms, whereas that of the hydrodynamic corral is several centimeters. Okay, so the sort of physical picture of 3 timescales is important to keep in mind as we try to link to de Broglie's mechanics. So there's this fast dynamics, which is the responsible. So this is the timescale of the bouncing of the drop, which is responsible for wave generation. And then you have this intermediate dynamic. So again, when you strobe, it's basically the time scale for this particle to explore the domain. Then you have the time scale of statistical convergence. And again, the remarkable thing of the system is we can actually visualize, we can actually measure on all 3 of these timescales. So again, this is they're bouncing about 50 hertz. So with a high-speed camera, you can see the fast dynamics, and you have to wait about an hour for the system to converge statistically. Okay, and so we all, Pedro Sainz looked at this, the motion in an elliptical corral. So here you see a particle, basically is very similar to the circular corral in terms of the mechanics. You basically have ultimately a correlation between position and speed. As a result, there's structure in the PDF. And he showed that you can have something analogous of statistical projection effects, and we'll hear more about that in his talk. The reason I want to point out this elliptical case is we noticed in that work that the average wave field looks, so at any given instant, the wave field is different from the mode of the cavity. So it's some complex thing, such as we see top left. But the average wave field looks very much like the particle histogram. Okay. So, and it turns out that both can be expressed as the sum of two modes. So this inspired the work of Matt Dury, who showed that the average wave field can be related to the particle histogram through a convolution. So you basically convolve the particle histogram with the wave field of a bouncer. So if you have a bouncer just bouncing in place, you convolve the PDF with that field and you get the average wave field. And of course, the bouncer wave field depends on memory. As the memory increases, it becomes larger in amplitude. But in any case, you see then, so why is this an important object, this average wave field? Because on average, that's the potential background potential that the particle is seeing, okay? And so in 1D simulation, so here you have a particle moving, so at relatively low memory, you can see that so the particle is just sloshing back and forth, or moving back and forth along a line. And here, so this is time along this axis, and you can see that the instantaneous wave field is sloshing in response to the particle motion. But at very high memory, it is not. It's the mean pilot wave field as indicated by these black curves. I should say on the right, at high memory, the instantaneous wave field converges to the mean. And so the particle is then basically exploring this background potential, which is non-local in the sense that it depends, it's prescribed by the statistics of the particle, okay? So I want to make this connection between the mean pilot wave field and the quantum potential in Bohmian mechanics. Okay, so we now really have three paradigms for macroscopic quantum behavior with the Walker system, and all of them depend critically on the resonance between the drop and the wave, because this is what's responsible for the quasi-monochromatic wave field and therefore the imposition of quantization, the emergence of quantized states. And so this particle then excites its own potential and then explores it, right? So it's basically navigating this. Of course, everything's local. I use non-local in the sense that one might misconstrue it if one didn't acknowledge that there was a pilot wave. So in any case, it basically excites a potential and then explores it. And as a result, so you get in orbital pilot wave dynamics, again, the quantized orbits emerge from the dynamic constraint imposed on the droplet by its quasi-monochromatic wave field. And then in the chaotic limit, you get this intermittent switching between weakly unstable periodic orbits. And the second paradigm we saw in the Friedel oscillations, you excite inline oscillations, and these inline oscillations actually have the Faraday wavelength. And so there's a signature imposed on the statistics by these inline oscillations. And then basically there's a chaotic regime in which, so in 1D, you get a sort of random walk where you have characteristic particle speed and a Faraday wavelength. And this then evokes Nelson's mechanics, stochastic mechanics. So we've seen this comes up in a number of theoretical models of walking drops, including those of Bacot and others. So we now have this growing grocery list of hydrodynamic quantum analogs. So here they are here, and various degrees of success. Some of them look precisely like quantum mechanics. Some look a little bit like quantum mechanics, but we see what the limitations are through exploring these analogs, and in particular, we know that viscous damping of the pilot wave is our enemy. So in all of these cases, the quantum features emerge at high memory. And there are also cases where the drop inertia can dominate the pilot wave force. And so spin states, for example, are unstable in the regime that we explored. And so how can we extend this? So we know that microscopic particles are not, fluid droplets bouncing on a silicon bath, but what essential features of this Walker system can we take and project into a generalized pilot wave framework, so we can then relax some of the limitations we have with the hydrodynamic system. So we retain the key features of the Walker system, in particular memory, resonance, and the resulting quasi-monochromatic wave field, and explore beyond the range of the hydrodynamic system. So this will not only allow us to try and find more analog systems, but it will allow us to hopefully connect and inform quantum pilot wave theories. Okay, so just the simplest the simplest generalization one can have is a parametric generalization. So if we take the stroboscopic trajectory equation and we non-dimensionalize it, then we see that they're just two dimensionless groups coming in. So the first is this, it's the non-dimensionalized memory. It basically tells you how close you are to the Faraday threshold. So so the gamma W is the walking threshold. So you're always above the walking threshold, but below the Faraday threshold. And the other parameter has all of the fluid systems. And that basically prescribes the inertia of the particle relative to drag and wave terms. And notably in the lab, this is strongly constrained. So certainly in the experiments we've looked at, kappa naught is between 0.8 and 1.6. So what if it's 10 to the 18 or 10 to the minus 18? Can we get more quantum-like features there? So for example, when are hydrodynamic spin states stable? When is a walking state unstable to inline oscillations, which we've seen is also a route to quantum-like statistics. So we have explored this generalized framework with Anand. We looked at the stability of spin states, and we found that in the low inertia, high memory limit, you can in fact get a stable spin state. And we've actually looked at this in 1D and 2D, and this is the summary slide for the two-dimensional case. So you see the spin region here. So this is high memory. So this is the Faraday threshold. This is the walking threshold, well, analog. And this is basically the drop inertia. So you again get spin states in the low inertia, high memory limit. And here in the 2D case, you get these wobbling and precessing orbits also. And then as the drop inertia increases, you get, if you perturb it's always laterally, it's always neutrally stable to lateral perturbation. So if you knock it to the side, it'll just keep going in a straight line. But if you perturb it in the direction of motion, then you'll get overdamped oscillations here, underdamped oscillations here. And then when you get into the, in 1D, you'll get a sort of random walk along a line. Here you get the sort of erratic motion, which gives rise to a sort of diffusive behavior. Okay, so that's basically how this class of dynamical systems behaves in general in 2D. So again, you do get richer structure, for example, spin states. And there are, of course, further generalizations which people have been exploring. So you can look at alternative waveforms. So here we've kept the Bessel form, but you could say, okay, what happens if we put in a sinusoid or Gaussian forms? And this is precisely what Matt Dury and the group, Tapio Simula's group in Australia has done, and we'll hear more about that later. And we can also extend it to 3D. So there are the physical pictures. You have a particle as a source of spherically symmetric waves, and at a certain point, it will become unstable and start moving, as is the case in 2D. Okay, and so you can also imagine adding in stochastic forcing. So in addition to this, so you then have a sort of hybrid pilot wave stochastic dynamics. And of course, again, the hope is that this, and we'll see that this can guide our intuition in terms of developing a sort of quantum pilot wave theory through extending the work of Bohm and de Broglie. Okay, so let's now try and connect to the quantum pilot wave theory. So the Madelung transformation, I'm sure you are all aware of. It's basically a polar transformation. So you substitute this form for the wave function into Schrodinger's equation, and out pops a hydrodynamic form. And the beauty of which is you've gotten I out of the equation, and H bar is now confined to a single term. And this is the quantum potential, and this is a curvature term. So it actually appears like just H bar appears as in this equation as does surface tension in the hydrodynamic case, where the waves are made by the influence of surface tension. Okay. But we're still just describing the statistics. So there's no dynamics. This is just a way to interpret the evolution of a quantum system hydrodynamically. In order to get trajectories in, you have to follow Bohm. So he said, let's set this particle velocity equal to the quantum velocity of probability, in which case you get this trajectory equation. And so you have the particle then moving in response to whatever classical potential might be there, and this non-local potential, this so-called quantum potential, which is defined in terms of the probability density. Okay, so basically it's a potential which depends on the statistics of the system, right? So this is again harkening back to our mean pilot wave potential. So in terms of problems, I'm not qualified. We have others here who are much better qualified to talk about Bohmian mechanics, but it is non-local, and this can be seen as a pro or a con depending on your camp. But it is non-local by virtue of the quantum potential. Okay, and so this is in fact why Bell sided with Bohmian mechanics. He said, well, Bell's theorem requires that any hidden variable theory be non-local, and Bohmian mechanics is non-local by virtue of this quantum potential. And there are other difficulties, in particular if you have a single mode in a quantum corral, it says that the particle won't move. But okay, so in response to some criticism, he soon after the publication of his early work, he combined with Vigier and suggested throwing in a stochastic forcing. So you have now this input from a subquantum realm. So then particles jostle about this quantum velocity of probability, like Brownian motion of gas molecules about streamlines. Okay, so now we have this non-local quantum potential, and then we have this slightly ad hoc stochastic forcing coming from the vacuum. And so if you compare Bohmian mechanics and Walker's, you see that so in all instances, the Faraday wavelength is playing the role of the de Broglie wavelength. But if we look at the guidance equation, so we have this local potential, which is the pilot wave potential. But notice that we can decompose that into a mean pilot wave potential, which is non-local. It involves the again the convolution of the bouncer wave field with the histogram. So it's basically prescribed by the statistics, therefore it's non-local. And this perturbation wave field, which is just the instantaneous difference between this mean wave field and the actual wave field. So it is actually local, but we have these two terms here, the sum of which, so you can really sort of associate this with the mean pilot wave potential with this non-local wave potential in Bohm's mechanics, and this perturbation wave field with this arbitrary ad hoc stochastic forcing, which is invoked by Bohm and Vigier. And so you can see how the connection might work. The other problem I see with Bohmian mechanics is there's no source of no wave source indicated. So with the Walkers, clearly the particle bouncing is responsible. And this then leads us to de Broglie's mechanics, which was rooted in a sort of intrinsic particle vibration. He saw particles as being basically having an internal clock at the Compton frequency. So why the Compton frequency? So this follows from so the Einstein-de Broglie relation, this from relativity, this from quantum mechanics. It defines this Compton frequency. And so de Broglie proposed that particles have an internal vibration at this frequency. This then plays the role of the bouncing in the droplets, and then the particles move in resonance with the guiding or pilot wave. So his is again a double solution. So you have this particle generated waveform, phi, which is responsible for guiding the particle, and then that gives rise to dynamics that somehow gives rise to statistics described by the standard wave function. Okay, and so he considered the guiding wave field as being the Klein-Gordon, and if you have a particle moving at uniform speed and it's dressed in a monochromatic wave field, then by definition the group velocity of that field has to match the particle velocity, and that's where P equals h bar k comes from. Okay, and he also stressed the importance of resonance in the system, so the sort of harmony of phases. Okay, and he didn't really specify the mechanism of wave generation, neither did he specify the form of the guiding wave, but you see very clearly the connections between our system and his. You basically, the bouncing drop plays the role of the internal clock. You have this intermediate dynamics, which is, so the basic motion of the object is described by P equals h bar k in his system. Then you have this convergence to the long-term statistical form. And there's some nice work by Thomas Duert's group on discussing the connection between the two. Okay, so you have this basic map between the two. So the bouncing plays the role of the internal vibration or the zitter. You have capillary wave fields in our system as opposed to matter waves. Surface tension is effectively playing the role of h bar, the Faraday wavelength, the role of de Broglie wavelength, and there's a second wavelength in quantum mechanics, which is the Compton length, and that's sort of the scale of the vibration. So we can think of that as being, say, the step size in our system. Okay? So what are the shortcomings of the pilot wave system? So of these quantum pilot wave theories, in my view, the mechanism for the pilot wave generation is not specified. So I see Bohmian mechanics as a dynamical reformulation of a statistical theory, and you have the particle being piloted by the statistical wave, and it's non-local in the sense that the particle is guided by the quantum potential. In de Broglie's mechanics, again, he originally said there are two waves. He tried various options for the guiding wave, but then ultimately just said the two are proportional. So then it really reduces to Bohmian mechanics. So the two have been conflated into one. So, and of course, a big question is, what is the matter wave field in quantum mechanics? So I think we'll be hearing from Anna Maria later, but workers in stochastic electrodynamics suggest an electromagnetic pilot wave. Others have suggested the Higgs field, gravity waves. I'm open to suggestions. Any wave will do as far as I'm concerned. But we thought we might follow de Broglie because the Klein-Gordon field is so close to the water wave equation. It's kind of nice to work with. And we know that this Klein-Gordon field equation actually describes the Higgs field. So we can ask ourselves, what might de Broglie have tried if he had had MATLAB? Okay. So this is actually one of many. So the beautiful thing about the Walkers is it's inspired all sorts of sort of rational classical models of quantum dynamics. I won't go through to them here, but it started with Anderson and Borghese, and then we'll be hearing from Aurélien a little later about their model. And I'll just talk a little briefly about our model, which we call hydrodynamic quantum field theory. And again, it's basically having a go at a rational dynamics by extending de Broglie's. De Broglie's mechanics informed by the pilot wave system, by the walking droplet system. And so this quote from Holland is, I think, very nice. It says, "We can envisage a more active role for the particle, something which is not even admitted as conceivable in the conventional view. This may, for instance, enter as a source of the pilot wave field through an inhomogeneous term in the wave equation." So that's really, I mean, that's of course what's happening in the hydrodynamic system. So let's follow that up. So this will work by Yuval Degan and later by Matt Dury, and we'll be hearing from Yuval later in the conference. So I won't steal his thunder, but I'll just sort of give you the spirit of it. We basically take Klein-Gordon and we put in a localized forcing corresponding to a particle vibrating at twice the Compton frequency. So it's basically the particle is then seen as an excitation in the Higgs field, and then the particle moves in response to gradients in wave amplitude. So this is the guidance equation, and sure enough, so at a critical coupling, so the only unknown here is this coupling constant. At a critical coupling constant, the particle starts moving, and so it's basically dressed with a wave which has the de Broglie wavelength. And it starts moving and again, because of this, what I described before, if you have a particle dressed in a monochromatic wave moving at the particle speed, if the wave satisfies Klein-Gordon, then P becomes h bar k. But you also get these inline oscillations, which are reminiscent of what we've seen in the hydrodynamic case, both in the lab and in the generalized framework. You get these inline oscillations, these modulations in speed with this frequency, with frequency ck, so that sort of gives you a dynamic interpretation of the relativistic quantum dispersion relation. So you have omega squared, you have the Compton frequency, which is a frequency of internal vibration, and then you have the frequency of inline oscillations. Okay, so these are both features of this so-called hydrodynamic quantum field theory. And if you extend it to 2D, as Matt Dury has done, you actually see that the waveform actually beautifully approaches, so in the non-relativistic limit, it basically approaches a plane wave with the de Broglie wavelength. Okay, and so in fact, so you have this you have waves, propagating waves with the Compton wavelength emanating from the particle, but then you have this de Broglie wavelength in a sort of planar form upstream of the particle, okay? And so that being the case, you expect, so how will this object diffract when it hits a slit, right? So you expect that this is very different in form from the Walker wave field, which has this sort of horseshoe shape. And so, for example, when we send it towards the slit, we expect quite a different diffraction pattern, okay? And so a few things I've learned. So this is all early doors, but we're excited to push it forward. And so what we see, and it's also, for me, it's allowed me to unravel the importance of like the role of the de Broglie wavelength and the Compton wavelength. So because the hydrodynamic system, there's only one wavelength, and it's the Faraday wavelength. In quantum mechanics, there are these two length scales. So what we see from this is that in the non-relativistic limit, the guiding wavelength is lambda b, and so the Faraday wavelength plays the role of the de Broglie wavelength in non-relativistic mechanics. But then in the relativistic limit, the de Broglie wavelength approaches lambda c, so you can see how the Faraday wavelength then so plays the role of the Compton wavelength effectively in relativistic quantum mechanics. So for example, you can get structure. So when you have these spin states, something zipping around in its own wave field, if you're looking at the relativistic case, that then looks like the classical model of the electron, which is a charge zipping around the Compton wavelength at the speed of light. Okay, and so, right, so this is, to wrap up, we've seen that this hydrodynamic system provides a vehicle for exploring the boundaries between classical and quantum mechanics, and it extends the range of classical systems to include features previously thought to be peculiar to the quantum realm. And I think most importantly, it provides a conceptual framework for understanding these features. So in particular, the thing I want to emphasize today is you can see how local hereditary mechanics, such as this walking droplet system, can give rise to features that appear to be spatially non-local if you don't acknowledge the fact that it's a pilot wave system. So 3 examples here. One, wave function collapse. That really is a non-problem when viewed from this perspective. We've seen action at a distance when we've seen the walkers interacting with submerged pillars or wells. So you basically can, we infer, again, action at a distance, but we know these are actually wave mediated forces. And also we have this notion of the mean pilot wave potential, playing the role of the quantum potential in Bohmian mechanics. Okay, and we've seen how this really does harken back and connected to Broglie's mechanics as well as other quantum hidden variable theories. And for me, it suggests how one can hope to build upon the work of de Broglie and Bohm. And it's motivating a new class of models of quantum dynamics, and we'll be hearing more about that later in the meeting. And for me, it suggests that the quantum paradoxes may ultimately be resolved through elucidation of pilot wave dynamics on the Compton scale. So in terms of where to next, so we're continuing to explore new HQAs, and again, and thereby assessing the potential and limitations of the Walker system. There's some interesting connections with active matter, including spin lattices, which Pedro Sainz will be talking about later in the meeting. I do think these quantitative comparisons between the Walker system and these other systems, so for example, SED, the Lorentz-Dirac equation, Bohmian mechanics would be very interesting and useful in terms of connecting the fields. And it's also a good way to get into a problem. If you're interested in sort of engaging in the field, writing a comparative study would be really useful. And so explorations of the generalized pilot wave framework in 2D, 3D, then these hydrodynamic quantum field theories, and taking the intuition gained from the Walker system and trying to extend de Broglie's work. And also refinement of language. So I remember Anna Maria at our last meeting in Brown said, what do you mean by quantum-like statistics? Good question. So we're trying to answer that question now. We're using machine learning to try and infer a sort of analog Schrodinger equation for walkers. And this is work being done with Nathan Kutz in Washington and Andre Nashbin. And so we're now, and also, of course, tiptoeing towards entanglement. So we'll be hearing more about this from those more qualified, including Louis, later in the meeting. But we know that when you have multiple particles, you can get collective behavior. So they become synchronized through their wave fields. So when do these states become non-separable, and when do we actually get entanglement? So let me just graphically, what I see is happening is the following. We started with quantum mechanics, classical mechanics, never the two shall meet, and then pilot wave hydrodynamics, so the Walker system of even Emmanuel was discovered, and it's sort of making, so these HQAs are making inroads into the quantum regime, and this is in turn inspired, so this system has inspired the sort of generalized pilot wave framework where we can hope to capture more quantum-like features, and that in turn connects to these hydrodynamic quantum field theories, which are informed by both the Walker system and the hidden variable theories of old. And so hopefully the idea is that these all continue to expand and we rid ourselves of the quantum paradoxes. So just to summarize, why I love the walking droplets, it's again slightly miraculous that the timescales of, so the fast timescale, the intermediate timescale, and this timescale of statistical convergence are all accessible in the lab. And it's also, of course, a macroscopic example of a particle moving in response to its own wave field. And this is very difficult to describe on the microscale. For example, the Lorentz-Dirac equation of electromagnetism has runaway solutions and all sorts of difficulties, presumably owing to the difficulty in resolving the dynamics on the particle scale. And of course, as we've seen, this connects to a number of hidden variable theories, which we'll be hearing more of. And of course, it also spans a wide range of disciplines, which is why this meeting is happening, is the fact that it's connected to philosophy of science. So but the range of this problem, it goes from experimental and theoretical fluid dynamics, which is of course my specialty, to dynamical systems and connections to E&M, quantum mechanics, history of quantum mechanics, and the philosophy of science. And for me, it provides a vehicle for revisiting quantum mechanics with a fresh perspective, a physical picture that might ultimately allow us to understand it. So I'll just end with 3 questions which are suitable for the philosophers in the audience, and I think they're useful to keep in mind. So how differently might quantum foundations have evolved had this fluid system been known to its founding fathers? That's question 1. Question 2, what are the chances that the quantum and fluid systems exhibit such similar behavior in so many cases for completely different reasons? And finally, what are the chances that in 1930, mankind correctly surmised that the micro and macroscopic worlds are philosophically distinct? And that's definitely a question for the philosophers. And with that, I'll end and just plug a recent review written with Anand Oza, where a number of the ideas presented here are developed in full. So I'll welcome any questions.